Hello. Hey, I have a viewer. Somebody's here. to the one person who's on here already, in the chat window, could you let me know if you could, number one, read what I put on the board, and two, which one of these two equations you can read? One of them's backwards, one of them's forwards. There should be a chat window. People are starting to come in. If you can hear me, please introduce yourself in the chat window. I think you can hear me. Can you hear me? Oh, we lost somebody. People are coming in. 10 people now. Can you hear me? If you can, please tell me in the group chat. Can you hear me? If so, tell me in the chat window. Okay. So the video hangout is not apparently allowing other people to respond inside my chat window. So I'm not seeing anybody in my chat. But when I pull up the live comment stream, I can see all of you, and so I'm assuming you can hear me, because that's what everybody is saying. It's just weird that it's not showing up in my chat window. I have to go to the webpage itself. That's bizarre. So, one person responded earlier, and I have these different things up on the board. I have each one written forwards and backwards. Which one can you see? Which volume can you see? Can you see the first one, or can you see the second one? I'm really hoping you can see the second. So if everybody could, if some people can respond so I know how I'm going to have to do this. So the top one or the bottom one? If you could respond. Also, let me know if you can't read what I'm doing. Yes! That makes me very happy. That means I can actually write normally. On my screen, the first volume is what's forwards. The second one is what's the second one's front forwards. But on my screen, the top one's forwards. Okay. Can you read my writing, or is the glare from everything too strong? Can you read this? If you can read my handwriting, I'll get started. Okay. I'll try to write big, and it seems like the closer I stand to the board, the more visible it is. Okay. It ain't broke, that's true. I'll try to be as best as I can. Okay. I'll try to write neater than I normally do as well. Okay. So before, when we were talking about in class, the idea that I was giving you a quiz and it didn't go so well, I didn't want you to feel like you can't do this well. So I wanted to do some more curve sketching as well to help you. So before we get started doing this stuff, there's a cool little chart in Thomas Transcendental Calculus that I think might help you when you go to plot. So as you remember, we've talked before about how an increasing function has a first derivative that is positive. So when you find that the first derivative is positive, you know that your function must be increasing. Likewise, if the derivative is negative, you know the function is decreasing. If you know that you have a maximum, so the first derivative is 0, the second derivative is negative, that means we have concavity that's down, up, down. Whereas positive concavity is up, up. And this becomes more clear when we see that the second derivative means stuff like this. And the second, and cut down means stuff like this. So when I go about to plot concave up and concave down, this is what helps me. And when I create maxes and mins, I make sure that I'm doing it at the right places. And by remembering some of these basic tools, and like stuff like points of inflection, points of inflection being either cup up going into cut down or cut down going into cut up. Using these tools, we can help make our graphs easier to analyze and create. So increasing means the first derivative is positive. Decreasing means the first derivative is negative. Maxes and mins occur when they change. So when it's equal to 0, then the concavity. Concavity is easy to sketch when we have here, but very frequently when we are dealing with concavity, we won't even really need to worry about sketching the concavity part, because as I've talked before, a lot of curve sketching is connecting the dots. So this becomes more of a check mechanism than an actual use, but it allows us an extra bit of understanding. And lastly, the point of inflection allows us to do this. So if I have a graph like y is equal to x cubed, the first derivative I get 3x squared, second derivative is equal to 6x. There's clearly not going to be any change from positive to negative in the first derivative, so I'm not going to have a max. I'm not going to have any kind of maxes or mins. But when I go to make my point of inflection at 0, I go from negative concavity to positive concavity. So down, up. And notice that that's the most defining piece of the x cubed graph, is that going down and going up of the concavity. And so by keeping these little things in our minds, we can do concavity and curve sketching a lot easier. So with those things in mind, I'm going to go through a couple of sketches, going through a couple of different graphs. I'm viewing this hangout sort of as a recitation. So from time to time, I'm going to be checking the chat window to see if you have any comments, how I'm doing it. Am I going too fast, too slow? If you have a particular function you would like me to graph, please let me know, and I will do so. And so I'll check periodically, and I will try to stay as close to the board as possible, because it seems like it focuses on the board better the closer I get to the board. And I do see that it is blurry, even on my screen. I can tell that it's blurry. It isn't as blurry if I don't move too much. And as you've noticed in class, I tend to move a lot. So I'll try not to be too crazy. Okay, let's start off with a simple sketch. Y is equal to 6 minus 2x, let's put a 2 here, 2x minus x squared. So with this x squared term, I notice that this is going to be my biggest derivative. This biggest derivative tells, because it's only 2, when I take two derivatives of this, I'm only going to have a negative concavity, which I already know means no points of inflection. So, as always, I'll tend to look forward first to go through the easiest things to take off the list. Number one, are there any asymptotes? Clearly, no asymptotes. Because there's no denominator. Next thing are zeros. I look and I see if I can factor. I look at and I factor 6 and negative 1 to see if there's any way I can get a negative 2 there. Well, 6 has the factors of 1 and 6, 2 and 3, and 1, and negative 1 has a difference of factors of 1 and negative 1. So it's going to be down to the 6. Are there any pairs of factors that have differences of 2? And there aren't. There's only one difference of 1. So if we were to find zeros, which we could, we would have to use the quadratic formula. So negative b, which is positive 2, plus or minus 4 plus 4 times 6 times 1. Notice the negative and the negative cancel out, all over negative 2. So that gives me 2 plus or minus the square root of 4 plus 24 over negative 2. So I'm going to deal with negative 2 plus or minus the square root of 28 over 2, negative 2. So that's going to be 2 plus or minus 2 square root of 7 over negative 2. Or the zeros are negative 1 plus or minus the square root of 7. So Karan's saying that maybe if you do full screen, that might help. A little bit better. Still very blurry. It seems better too. Okay. So I'm going to erase this. Now notice -1 plus or minus 7. That's going to be somewhere in the ballpark. Square root of 7 is somewhere in the ballpark of 3. It's just under 3 since the square root of 7, square root of 9, which is just bigger than 7, is 3. So we're looking at numbers roughly at -4 and 1. Sorry, 2. In both cases, they're going to be slightly closer to the origin. Okay, so the zeros are the easiest part. Not necessarily. The easiest part would be to take the first derivative. So do that. We get -2 minus 2x. So we can set that equal to 0. We get -2 minus 2x. Or 2 is equal to -2x. Or -1 is equal to x. So my critical point is -1. Plug in values in, for example, by choosing number 0 and number -10, it's very clear that this becomes positive and this becomes negative, which means that this is unmatched. And f of -1 is 6 plus 2 minus 1, or 7. Okay, the last thing that we need to do is take care of the second derivative. Now, I've already seen the intuition of where it's going to go. You probably have seen it too. Y double prime would just be -2. So if I make my number line, which remember you need to label your number lines, that's always -2. So I always have a negative concavity. So I can label these concave up, never, concave down, all real numbers, increasing from -infinity to -1, decreasing from -1 to plus. So we are on our last step, which is to graph this sucker, to sketch it. So Take a look at my possibility of this graph. I plug in that point at 7. Now, if you remember from before, when I was taking a look, at a max, I already know that it curves down. So I can cut down here. I don't know everything about it yet, but I know that it cuts down. I also know that if I plug 0 in to here, I'm going to get 6. Likewise, if I plug it into 2, I get that as well. Since I know it's cut down, I have a bigger cut. And for my other work, I see that the zeros are going to be right about at -4 as well as at +2, just before it. So I can make a plot like so. Notice, this is a very ugly parabola. And as I always say, assume my drawing is terrible. But the main part of this thing, in which you would normally use this kind of sketch, if you were to make it in a more real situation, is you're more looking for the behavior of the function. You're not so much looking to make it pretty. If you can make it pretty, that's awesome, but it's not a necessary component. Otherwise, I would have failed out of my calculus class. Okay. That's one of the more simpler examples. Let's take one step up. You can't see that. The very top of your screen, you should be able to see y is equal to x cubed minus 3x plus 3. So once again, I look at my biggest order term and I think to myself, am I going to have to deal with points of inflection, a concavity? It's bigger than a quadratic, it's at least a cubic, therefore there will be some concavity going. I hope and pray that it's easy to solve for, because clearly zeros are an unknown factor, at least in our current line of work with our things. We could use different methods to find a zero. In Calc 111, you can find that. But at this moment, we don't have the tools. We also, once again, have no asymptotes. That's interesting. I think I might have a slant going on with my computer, making it even worse. So, we go straight for the kill, go straight for the derivatives. That's fairly straightforward. Factor out of 3. Easy to factor out. We have 3 times x plus 1 times x minus 1 equals 0. So my two critical points would be plus and minus 1. Also very easy to do the first derivative test like last time. Choose a really big negative number. It'll easily overpower my +1 and -1, so I'll clearly get a negative. Choose a really big positive number. It'll clearly overwhelm both the +1 and -1. Sorry, it'll be positive. So negative, negative is positive, positive, positive is positive. In between, I choose a number in between +1 and -1. That's easy, 0. 3 times 1 times -1 is clearly negative. So I have a max here, and I evaluate at the 2 points. Y of -1 becomes -1 plus 3 plus 3, so that's 5. Plug in +1, I get 1 minus 3 plus 3, which is 2, 1. So one thing also to note, that whereas my domain is from -infinity to infinity, my range is also from -infinity to infinity because it's an odd function. So I've already got most of the idea of what's going on with my graph. What's left to do is to try to figure out what kind of concavity is going on. Now I'm thinking that since the two critical points are +1 and -1, the point of inflection will be halfway in between. I'm not sure, but it seems like a reasonable guess. And if I take my second derivative, I see that I'm right. And my point of inflection occurs, plug 0, at my y-intercept of 3. So let's put this all together. Since we're dealing with mostly positives, we have this case. Our biggest number occurs here. Our local min occurs here. We also know there's a point of inflection here. It goes from a positive concavity to a negative concavity. So it's going to be like so, a little curve up. I know that I have a max here, so it cups down. I have a min here, so it cups up. And we play connect the dots. Notice since I don't know where the 0 is, I don't know where it crosses. And that's okay. If we really wanted to know, we could start plugging in other numbers into the function to see between what two whole numbers there. Sorry. Yes, somebody made the comment that it should be negative and positive. You're quite right. I put it down wrong, but I ended up doing my sketch right. So quite right, Richard. I want to do one more polynomial before we get to the exercise that Jonathan suggested or asked for. The most important thing I'm looking for on these are you finding the maxes and mins. I would love for you also to be an expert in curve sketching. I don't know how much you're going to test on the exam, the final exam. I do know that there's going to be maxes and mins on the exam. On the first number line, that was y prime. So the function, remember the function was increasing, then decreasing, then increasing. First number line, so it would have been positive, negative, positive, because it starts off increasing, then decreases, and then increases. Okay. Y is equal to 1 minus x plus 1 quantity cubed. This looks disgusting. It's really not, as long as we use the chain rule. Once again, we have no asymptote, so I'm not going to bother writing it this time. But we do have a 0. And as long as we're careful about it, we can actually solve it very simply. Remember, we're looking for the x value. So by solving for the x value, or what the outside is, equals to 1, we can easily find the 0. So take the cube root of both sides. We get z plus 1 is equal to still 1. So z is equal to 0. Straightforward. No asymptotes, so we go straight for the first derivative. Well, the derivative of 1 is obviously 0. Do the chain rule. Negative 3 x plus 1 quantity squared times 1 for the inside. Notice this is very easy to solve for 0. We just get c plus 1 is equal to 0, or c is equal to negative 1. But look at this, it is squared. So if I look at my number line, since it's a negative times a positive, my number line will always be negative. So if I choose a really big negative, it'll still be negative no matter what's going on. So I have a function that's always decreasing, which I could have known by looking at the negative cubic and known that a negative cubic always is decreasing. But something interesting looks like it's happening at negative 1, probably my point of deflection. So take another derivative. Simple enough, we get negative 6 x plus 1, and indeed we're going to get a point of deflection. And x plus 1 is equal to 0, or a is equal to negative 1. This time I'll be a little bit more careful about my signs because I made a mistake the last time. So if I plug in a negative number, I get a negative times a negative, which is a positive. Plug in a positive number, I get a negative. So my initial guess was correct. Something to, so my initial guess of it looking like this is correct. It's just a matter of plugging everything in. Notice we have a 0 at 0. So that's also going to be our y and x intercepts. We also know that if we plug in -1, we're going to get 1 minus 0 cubed, or 1. This is going to be a fairly simple graph to draw. There's only two real points that we need to really care about. 0, 0, -1, 1. There's a point of inflection, so it goes cups up to the left, cups down to the right. Connect the dots. And that's all I really care about. If I erase this, I could possibly make the graph look a little bit prettier. But this gives us a general idea. It is still a cubic. It still hits at 0, 0. It still has a point of inflection at -1, 1. So if we wanted to, we could start labeling them at their points here. Okay. Let's see here. Jonathan mentioned one. I like it. He said f of x is equal to e to 2x minus e to plus or minus plus e to the negative x. Causing it to drift up again. It's a little bit better. So we take a look at this and we see if there's any asymptotes. Well, we're taking a look at these two different graphs. We need to consider what these two graphs naturally look like. E to the 2x is a graph that crosses at 1 and goes up. E to the negative x is a function that does the opposite. So if we add these two together, well, separately, and like this one, e to the 2x has a horizontal asymptote y is equal to 0 over here, and over here, it has y is equal to 0 over here. If I add these two together, notice that this added to this makes this asymptote go away. You have a positive infinity over here and a 0 here. Positive infinity plus 0 is going to be positive infinity. If I go to the right, I have a horizontal asymptote here, but this plus this cancels out the horizontal asymptote. Can't really make any more exact mathematical reasons yet because we haven't talked about limits in their math 111 case, in the infinite limits. So when you get into 111, I can give you a more precise notation of what I mean. But until then, I'll just make these qualitative behaviors. So then 0 plus infinity cancels out that horizontal asymptote. Infinity plus 0 cancels out that asymptote. But be very careful about these qualitative ideas because they can bring you down a dark road very quickly. So, we take a look at our graph, and we say, does this graph have any zeros? The first guess would be no. We have two things that are added together, the exponential functions, they're weird. And it's possible that there won't be any zeros. But I do notice something interesting. I have e to the negative x here, which means I could have an asymptote. Or I could have a weird zero idea. So I take my graph, and I have e to the 2x. That's actually, this e to the 2x plus 1 over e to the x. So this is the same thing as e to the 3x plus 1 over e to the x. And unfortunately, there's a glare right there. And if I try to block it, hey, there it goes. So I have e to the 3x plus 1 over e to the x. Well, e to the x can never equal to 0. So that cancels that idea. So I have no vertical asymptotes. I go to the top. See if there's any zeros. Is e to the 3x plus 1 equal to 0? Well, that would imply e to the 3x is equal to negative 1. Now, if e to the 3x can never equal to 0, there's no chance that it can equal to a negative number. So, clearly that's not the case. We have no zeros or asymptotes. So, we go straight for the derivatives. And there's no way I'm using this because I don't like quotient rule. I avoid it like the plague. So let's go back to the original function. E to the 2x plus e to the negative x. That's fairly straightforward. E to the 2x is going to be 2e to the 2x. This is a chain rule. E to the 2x, the outside its derivative is e to the x. Derivative of the inside, 2x, derivative is 2. Same thing occurs here, and we get e to the negative e to the negative x. Now we might be able to get away with some zeros. So, same trick as before. 2e to the 2x minus 1 over e to the x. This time we have 2e to the 3x minus 1 over e to the x. Well, we can't get any, does not exist, no zeros on the bottom. But we can get 2e to the 3x equal to 1. It's e to the 3x is equal to 1/2. So take the log of both sides. We get 3x is equal to natural log of 1/2, which using our log rules, we say natural log of 1 minus natural log of 2, and natural log of 1 is 0. So we have 3x is equal to negative natural log of 2. So x is equal to negative 1/3 natural log of 2, or if you prefer, negative natural log of 2 to the 1/3 power. So here comes the fun part. Is that a max or min? I don't know. It might be easier if we do the second derivative test. Because trying to do the first derivative test might suck. So, take the second derivative. We get 4e to the 2x plus e to the negative x. We take a look at that function. 4e to the 2x is always positive. E to the negative x, while annoying, is still always positive. Positive plus a positive is always greater than 0. And if we remember, we have cup up. So that tells me that I have a minimum. and that negative natural log of 2, 1 over 3. So one more interesting little bit we need to consider. Is this a positive number or is this a negative number? The answer is, that's no. That's not the answer to my question. Sorry. The answer is, I have to look at what the base is. So log base e of 2 is equal to natural log of 2. Wow, it's constantly adjusting now, ain't it? There. So we have natural log base e of 2 is equal to natural log of 2. So we need to remember, what is e? E is roughly 2.718, or 2.717. I'm going to do 2.7 because that's good enough. Now, so that's telling me, this is telling me that I'm looking at e to what power is equal to 2. So if I plug in x is equal to 0, I get 1. If I plug in e is equal to 1, I get roughly 2.72. So this number is somewhere in between 1 and 2, 0 and 1, so that means it's a positive number. It's going to be really small, so multiplied by my negative, by my 1/3 up front here, 1/3 times a really small positive number times a negative number tells me that it's barely negative, but it is negative. So, what do we do when we put this all together? We also can plug in and find our y-intercept. Plug in x equals to 0, we get 1 plus 1, which is equal to 2. We also need to be able to find our minimum value, so we plug in the disgusting mess. So this is equal to natural log of 2 to the negative 1/3 power. So we plug in y is equal to natural log of 2 to the negative 1/3 power. Which we're going to have over there, funny. So that's going to be e to the 2 natural log of 2 to the negative 1/3 power plus e to the negative natural log of 2 to the negative 1/3 power. It does quite make it. So that's equal to bring the 2 up, we get e to the natural log of 2 to the negative 2/3 power plus e to the natural log of 2 to the 1/3 power. The negatives cancel out. So I'm going to get the natural logs cancel out. So I have 2 to the negative 2/3 power plus 2 to the 1/3 power. Wouldn't it be nice if they cancel out? But they don't. So 1 over 4 to the 1/3 power plus 2 to the 1/3 power. So there's nothing more we can really do to that, unfortunately. At best, I might be able to say that this is 1 plus 2 over 4 to the 1/3 power, or 3 over 4 to the 1/3 power, which you can't see. But honestly, stopping it right there would be fine. So let's plug these numbers in. This is equal to, so this crosses. Basically looks like a parabola. Because remember, there's no points of inflection, always has a positive concavity, has a weird min, but in effect, this looks like a parabola, which makes sense because we added those two different equations together that canceled out the horizontal asymptotes. So Jonathan's asking, how did I get the natural log? So the natural log comes from the top here. When I take the top, I set it equal to 0 in order to find where the critical point would be. So I set the top equal to 0, and I got 2e to the 3x is equal to 1. Move the 2 over, I get e to the 3x is equal to 1 half. The only way to get rid of that e in order to get to the x up here is to take the natural log of both sides. The natural log of e to the 3x is 3x. The natural log of 1 half is natural log of 1 half. But remember, we have an identity. ln, can you see that? No. Natural log of a over b is equal to natural log of a minus natural log of b. Wow, that might help a little. So I have natural log of 1 half, that means it's natural log of 1 minus natural log of 2, but natural log of 1 is always 0. So I get natural log of 2, negative natural log of 2. This whole time, I could have left it as natural log of 1 half though. But I don't like taking natural logs of the powers. I could have also noticed, since this is natural log of 1 half, this is natural log of 2 to the negative 1 power. So I could have moved the negative 1, negative half. However you prefer. I prefer using the log rule like this because it's more simple to me. Okay. Let's see any other questions for now. So I'm going to put up another question up on the board. Okay. Let's have some fun. End off curve sketching with a bang. But you can see that. Y is equal to e to the x over x. Well, can this ever equal to 0? It's a good question. But remember, when we're dealing with this, when looking at the zeros, can e to the x ever equal to 0? So all we're caring about is the numerator at first. E to the x never equals to 0. It has an asymptote, but it never actually hits. So we have no zeros. But we do this time have a denominator, so we will be able to have an asymptote. Look, the bottom is equal to 0. Clearly, this is going to have a vertical asymptote. At x is equal to 0. It is snowing outside. Relax. Okay. Take the first derivative, or I could write this as e to the x, x to the negative 1, because neener, now I don't have to use the quotient rule. Derivative of the first, simple enough, times the first, times the derivative of the second, so that's negative x to the negative 2. So we have e to the x over x minus e to the x over x squared. So we're going to get x e to the x minus e to the x over x squared, lots of x's. So that's going to be x minus 1 times e to the x over x squared. So when we start looking for our critical points, we're going to look for when the top and bottom equal to 0. Because we have a denominator, so we can't look at when the bottom is equal to 0. But the thing is, the bottom equals to 0 only when it's outside the domain, only on our vertical asymptote. So I ignore this. I only care about when the top is equal to 0. Now, this also makes our job easier because we have x minus 1, e to the x is equal to 0. E to the x never equals to 0, otherwise we would have had a 0. Therefore, we just have to focus on the x minus 1 term. When is x minus 1 equal to 0? X is equal to 1. Notice this makes doing our first derivative test very easy. The only thing we have to be careful about, the bottom term. So we need to include all those points where they don't exist on our number line, even if they're really annoying and don't do anything. So we have 1 point, 0, another point at 1. Oh, so 0 doesn't exist. Okay? So choose a really big negative number. Negative 1 million. Negative 1 million minus 1, still negative number. E to a negative number, still a positive number. Negative times a positive is a negative. So we look at the bottom. Negative 1 million squared is positive. So negative times a positive divided by a positive is still negative. We do this again on the other side of x is equal to 0. Choose a number between 0 and 1, say 1/2. 1/2 minus 1, x isn't quite big enough, so it's still negative. But the other terms are all still positive. So I have a negative times a positive over a positive. Still negative. So we're still decreasing. All the way down to 1, because at 1, choose a really big positive number beyond that 0.1. 1,000 minus 1 is positive, finally. E to the positive 1,000 is positive. 1,000 squared is still positive. Positive, positive over a positive. Positive. So we're going to have a min of x is equal to 1. Nifty little sucker. So take a look at that. Plug in 1, we will see that that value, y of 1, e to the 1 over 1 is equal to e, which you remember is 2.72. Now we need to check to see if we have any points of inflection. Happy, happy, joy, joy. So I go back to my original case here. This is x to the negative 1. I can do either the quotient rule or I can do two product rules, neither which sound very enjoyable. I do know what this derivative is. So this derivative is this whole thing, because this was our original function. So that makes our life easier. I could have written this as y minus e to the x. So in that case, I only really have to do one product. And we are going to go optimization after this, by the way. So go for y double prime, we get y prime minus e to the x to the negative 2, plus 2 e to the x to the negative 3. So this is going to be e to the x to the minus 1, minus e to the x minus 2, minus e to the x minus 2, plus 2 e to the x to the negative 3. Notice this just comes directly from here. So e to the x over x minus 2e to the x over x squared plus 2e. Where's that? Yeah, 2e to the x over x cubed. So I'm going to get x squared e to the x minus 2x e to the x plus 2 e to the x over x cubed, or e to the x squared minus 2x plus 2 is equal over x cubed. So it looks like we have 2 points of inflection. Unfortunately, we're not going to be able to easily solve for this. I could use the quadratic formula, which isn't very nice. I could also notice that if I take an x squared, can you see that? Wait, okay. 5x squared minus 2x plus 2. See that? Then I can also separate it like so. Yes? But notice x squared minus 2x plus 1 is the same thing as x minus 1 squared plus 1. Move this to the other side. Now, if I was to solve for this, I would have to take the square root. But I come across the problem. You can't take the square root of a negative number. This just doesn't make sense. Therefore, I have no points of inflection. It must always be. Because this is always bigger than negative 1, therefore this must be always bigger than 0, bigger than 0, bigger than 0. So my second derivative must always be positive there, on top at least. And that's where the interesting thing comes in, because we still have to take in part our x cubed. So while the top is always positive, the bottom isn't. Not a point of inflection, but maybe a line of inflection. So we have a critical point at x is equal to 1. We have a line of inflection at x is equal to 0. We have a vertical asymptote at x is equal to 0. Question is, do we also have a horizontal asymptote? I never answered that. Where do I want to put it? I want to make a graph here. So we take a look at e to the x. Remember, horizontal asymptotes occur when x goes to the extremes. So if I choose a really big x value, a really positive x value, e to the x goes to infinity. E to the positive infinity. Any exponential function to some positive, really big value is going to be infinity. So infinity, even over the positive infinity there, we don't really know what's going to happen. It's going to go really fast. Let me tell you, it doesn't go to. But on the left-hand side, when I plug in e to some negative number, remember e to the x goes really, really small. And x going really big in the negative direction tells me that that's going smaller and smaller and smaller, but being divided into more and more parts. So this is going to go, so I have a horizontal asymptote of y is equal to 0 as x goes to infinity. So on this side, we have a function that has a horizontal asymptote over here and starts looking like this. But we also have a vertical asymptote over here. And since we know from over here, since we know that we have decreasing over here, as I go from this asymptote and approach this asymptote, I know which infinity this is going to go to. It must go from this to here, but it also must be decreasing the entire time. So I don't know how fast. It might get really close to 0 before it starts blowing. But I do know it's going to curve down, which, by the way, looks like concavity. Like I said, connect the dots. The concavity tends to fit into whatever dots you have. So the only thing I'm left with is this sucker. Now, once again, I have a decreasing function from 0 to 1. So if it's decreasing from one of the infinities, you can't decrease from negative infinity. It's already too small. But I can decrease from positive infinity. Makes sense because I'm going into a minimum. And after that point, I'm supposed to increase. Makes sense? It's a minimum. So my graph, my sketch, looks roughly like this. Notice negative concavity, positive concavity, decreasing, decreasing, increasing. So that's curve sketching. Let's do optimization. For each one of these, remember I have certain basic rules and ideas that try to help you. Step one, picture. Step two, so you first draw the picture of what you're going to do. Step two, you choose your variables. Take a look at your picture, choose which variables to be useful. So if I'm talking about a circle, side length isn't going to be helpful, but radius would. Circumference, maybe. Three, so I have picture, variables. Equation is my next step. So just looking at your variables, which equation will properly connect all your different variables. Step four, differentiate. Step five, solve. So using these basic tools, we can solve any optimization problem, any difficulty. The only thing that's going to be clever about optimization is going to be what equations to use. That's the hardest part. The second hardest part will be drawing a picture that accurately describes it. Because if you know what the picture looks like, you can look at an equation, you can set up different variables. Different variables will allow you to do the right equation. The right equation is easy to solve once you have, it's easy to solve something once you have the derivative. So we've done some cases. Okay, so let's do something simple. I did something simple in class already, but I want to do it again just so we can look at it. If we have the sum of two numbers is equal to 300, and snow outside, really making it weird. So the sum of two numbers is equal to 300, and I want to maximize their product. There's no picture that can go along with this very well. So I need to describe the equation as best as I can. Sum of two numbers. I kind of skipped step one because there's no picture. So I go immediately to two. Choose my variables. Let x be first number, and let y be my second number. Fairly straightforward. So step three, the sum of those two numbers, x plus y, is equal to 300. And then I need the product. So I want to maximize x, y. So I also need to consider, before I go to solve this, what is going to be the max that x and y can be. So it's a sum of two numbers. The biggest that x and y can be would be 300. So it's easy to think of one variable at a time. If x is equal to a 300, the max that it can be, what would y be? Clearly, y, if x plus y is equal to 300, the biggest that y could possibly be would be 0. And likewise, if y was 300, x would clearly be, if y was 300, then x would be 0. The linear combination between the two. So the equation that we want is product in this. But before I go to differentiate and solve, I can make my equation much easier to solve. trying to avoid that one spot there. I can rewrite y in terms of x. Y is equal to 300 minus x. Simple enough. Plug into my product equation. Product is equal to x. 300 minus x, or 300x minus x squared. Now we can take the derivative. dp dx is equal to 300 minus 2x. We set that equal to 0. It's fairly straightforward what this will be. This is going to be 300 minus 2 is equal to 2x, or 150 is equal to x, which makes y also 150. So, when I do this, this works not only for these kind of sums like this, but also in terms of our pictures. So, I can also take a look at a rectangle and put it inside of a triangle. And I want to know what is the maximum area that this rectangle can handle. So this is an interesting problem. And so in order to get more information about this, we also have to know more about the problem itself. So where does it hit the axis? Here, here, and here. Where do they hit the different lines? Well, it becomes fairly straightforward if we know that this is the point 1, 0, this is the point 0, 1, and this is the point -1, 0. There we go. We can get a little bit better off the layer. So we need to be able to take a look at our function. We have a good picture now, but we need to start looking at different variables that might be interesting. So we're going to be talking about area, so it's good to be talking about terms of length and width. And if we're talking about length and width, what better variables to use than x and y? But we have to be careful how we choose our x and y, because how we choose them in this case might make our problem easier to solve. See, by looking at this, I clearly see that this is an isosceles triangle. So this tells me, by the isosceles idea of the isosceles triangle, that if this over here will have the same y value as over here, the only thing that'll be different between this point and this point is going to be the sign of the x value. They'll be the same x value because it's an isosceles triangle. So if I move down this triangle, notice that I'm moving equally across both. The only thing that I have to be careful about is how I choose my x value. And because however much I move to this side, I'll move the same this side. So if I choose x instead of being the coordinate, the x coordinate of the top right of the triangle of the rectangle, it makes it easier. X coordinate top right vertex of rectangle. We let y be the y coordinate. and so on and so forth. So right now you might be thinking, why did I choose these two? I'm going to hope to show you in just a second. Now, as I look at my x value right here, I have this line. It's very straightforward to find the equations of this line. That when we do this, it's fairly straightforward to do this. The equation of this line clearly is decreasing at a slope of -1. It also has a y-intercept of +1. So clearly this line is y is equal to at 1 minus x. So this already gives us an equation to plug in for our x value. We can rewrite our y value in terms of our x value. If we're clever, we can also already have an equation for our area. Because when we look at my rectangle, this rectangle goes to the right, x, and to the left, x. Which tells me that my overall width is 2x. Or my length is, however you want to call it. I'm going to call it the width. Length is clearly how tall it is. Clearly, that's going to be y. But I already know what y is in terms of x. It's 1 minus x. If I choose a positive x value. So here becomes the clever part that I have to choose, because x is the coordinate of the top right vertex. Clearly, the smallest that x can be, for the top right vertex, is anywhere on this line. So x has to be between 0 and 1. Also, that also keeps y in the same range, because clearly y has to be a positive number. So I plug this into my area. Area is equal to 1 minus x times 2x, or 2x minus 2x squared. Easy to take the derivative of this. dA dx is equal to 2 minus 4x. Set that equal to 0. 2 is equal to 4x. X is equal to 1. So note how I did this. I drew the picture, and I got the intuition that since this is an isosceles right triangle, that I could break up my rectangle into two smaller parts. And so I chose the x coordinate of the top right vertex as one variable, and my y coordinate is the y coordinate of the same vertex as my other variable. Because I looked at the area equation, length times width, and noticed that this would be an important combination. So, doing this, I was able to find the width being 2x, and the length being 1 minus x, because this line is 1 minus x. Combination, plug the sucker in, it becomes 2x minus 2x squared, differentiate, and solve for x. Now, you could have also noticed, since just taken the area of one of these and maximized it, and you would have gotten the same answer if you multiplied by 2. Notice that that factor of 2 didn't change anything when it came to the overall answer. All that it changed was the area itself. So if you wanted to know what the maximum area was, that 2 would be an important term. But if you weren't looking for the area, you were just looking for the coordinates of x and y, then it wouldn't matter if you would just include the 2. So, answer to Ariel, will I be able to watch all this later? Yes, it will be the same link, just I won't be live anymore. Answer, do we have homework due when we come back from break? Yes, it'll be the same things that we've gone over from before. You're going to be doing second derivative. Wait, you actually just turned in homework for. You turned in homework already. You turned in homework for the second derivative test. The only homework that you'll be turning in for this over break will be optimization. Okay. So this problem is I personally like a lot. One of the classes, it might not have been yours, we talked about a box. I'm going to give some prep work on the other one. We talked about a box. And we were trying to make a box from a single piece of cardboard by cutting the box, corners out of the box of certain corners. So all these lengths are x. And we took the box and we folded up the sides to make an open-sided, open box, and we were trying to maximize the volume. And we had a certain length. A certain length and a width of 12 inches. And we were trying to find the biggest box we could. So when we took a look at the bottom, because we're folding up each of these sides, all that's left on the bottom is this boxed in area. That boxed in area, remember, the original length and width were 12. But I took off an x from the right and x from the left, although from your side this is the right. That's 12 minus x, or length being 12 minus 2x. Same thing being the width being 12 minus 2x. But notice on each one of the sides that I'm holding up, it has a height of x. So my height would be x. So when I plugged all this together with volume, I had x and 12 minus 2x squared. And I went through this whole problem and I solved it. I'm going to do this really quickly because I've done it in one of the classes already. I'm going to do a harder version of this problem. Just a second. The d dx is equal to 12 minus 2x quantity squared plus 2x 12 minus 2x minus 2. You reach all the way over there. So this becomes, if I factor out a 12 minus 2x, I'm left with another 12 minus 2x in the first term, but the negative 2 and the 2x combined into 4. So I get a 12 minus 2x, 12 minus 6x. Now this goes to the interesting part that's going on with this problem. How big can I cut from my box? Clearly, I don't have to cut anything from my box. And that's the smallest I can do because I can't add to my box. It doesn't make sense. So my smallest volume value for x is going to be 0. What's the most I can cut out of the box? Well, if I'm cutting from the right and from the left, the biggest that I can cut out is 2x is equal to 12, which is x is equal to 6. So when I look at my two critical points down below, I'm going to clearly get x equal to 6 for the first term, and get x equal to 2 for the second term. Now, if I cut all the box away, clearly I'm not going to have any box left. So that's not going to be an important point. But x is equal to 2 will. So that's the only point I really have to pay attention to. But if I went and plotted my first derivative test, remember the biggest it can be is 0, the smallest it can be 6, notice on my line, my number line, my number line does not extend to infinity in each direction. I chose my endpoints here to force my hand. So while the derivative is 0 at 6, it clearly doesn't matter because that's going to be 0 and 0 here. If I look and I take a point, say even just plugging in 0, my endpoint over here, 12 minus 0, 12 minus 0 is positive. If I plug in a number between 2 and 6, I'll get a negative. So say 4, 12 minus 8, 12 minus 24. That's going to be a negative. So I clearly have the positive that I was expecting it to. Notice that when you get your answers and you set up your optimization problems correctly, you'll notice that the answers tend to be fairly obvious which ones they are. If they aren't obvious, you can always plug in and use your first and second derivative test to your own advantage. So we check in, we plug the value of x is equal to 2 in. We're clearly going to get 2, 12 minus 4 quantity squared, 2 times 12 minus 4 is 8. So that's 64 times 2, which is 128 cubic inches. So the biggest my box could be in this case is 128 cubic inches if I cut out 2-inch squares, 2-inch by 2-inch squares from this side of the box. So this is an interesting problem. I really like it. You might have seen it already before because in one of the classes I did it, one of the classes I did it time to. But here's a more interesting version of the problem, which, as you know by now, means run away kicking and screaming. So let's say we have that same box. But first, not the same box. Let's say we have a box. But here's the thing. This time, I don't want to have an open top. Because this time, I want to build a suitcase. So we start off with a piece of heavy-duty cardboard. And I have a box that's 36 inches by 24 inches. Since I want my box to have a top, I decide to fold this. Fold this box, and I cut it the same way I did before. But only this time, the top of the box and the bottom of the box will not be the same. Since I folded this in half, the bottom will be 18 inches long. The top and bottom will be 24 inches. I'm still cutting out corners here. They're all the same size. This time, when I unfold it, it's going to be an interesting, more interesting shape. It would be a more interesting shape. Because when I went about to actually unfold this, I have my original shape. Attached to itself. This is a length x, but now, as another length x, add 2. So, once again, our same tools are applicable. This length across the top here will be 18 minus 2x. This height, I need to write that right here, 18 minus 2x. This height right here is going to be 24 minus 2x. So the same thing will be held true here. So when I make my enclosed box, I need to also be able to figure out what each one of the different sides is. So if I set this center part as a length 2x here, as the base, I fold these up like so, and these will fold over. You'll notice this will make a complete box once completely sealed. This complete box, as I said before, this whole length is simply 2x. So I now have all three equations once more. Length, 2x. Width, 24 minus 2x. Height, 18 minus 2x. So remember the base, cross is 2x. Remember over here, 24 minus 2x is the full length of the base here. And I'm folding up this side up. So that's 18 minus 2x. Multiply them all together, and I get volume. Pull out 2's everywhere. I'm going to get 8x 12 minus x 9 minus x. So 8x 108 minus 21x. That's x squared. So that's going to be 864x minus 168x squared plus 8x. While discussing with huge terms, the math itself is very straightforward. Differentiate, get 864 minus 336 plus 24x cubed x squared. If I remember right, 864 is divisible by 24. So use my handy dandy calculator on my phone. Hope and pray that I'm right. I am. It's 36. To factor out of 24, I get 36 minus, need to factor out of 24 from 336. That's 14. So I have the derivative is equal to 24 times 36 minus 14x plus x squared. And I look, do the factors of 36 have two factors that add up to 14. So that's going to be 2 and 18. Nope. 3 and 12. Nope. 4 and 9. Nope. 4 and 9, nope. 6 and 6, nope. So we need to look at a quadratic equation. Or we can complete the square. I'm going to complete the square. So I'm going to erase my original picture, so I have room here. (36) minus 14 plus 14x plus x squared is equal to 0. Move the 36 to the other side, I get x squared minus 14x is negative 36. The middle of this, whoop, you can't see that. Still can't see that. So x squared minus 14x is equal to negative 36. Take 14, divide by 2, that's 7 squared is x squared minus 14x plus 49 to both sides. I'm going to get x minus 7 quantity squared is equal to 49 minus 36. That is 13. Square root both sides. X minus 7 is equal to plus or minus the square root of 13. X is equal to 7 plus or minus the square root of 13. Much easier than the quadratic formula. Well, maybe not easier, but more straightforward. Remember, square root of 13 is in between square root of 9 and square root of 16. So that's between 3 and 4. So clearly, x in both cases will be positive. So when I look back at my original case, over here, I have 7 plus square root of 13 minus x, 7 minus square root of 13 minus x, and I can take and I can factor this and use my number line. The smallest it can be is 0, cutting nothing away. The biggest that I can cut away by looking at my terms right here. The biggest I can do is I have no limit here. 24 minus 2x is equal to 0 at 12. So the biggest here is 12. The biggest here is 9. So the biggest I can cut away is 9 inches. So take a look there. I have 7 minus the square root of 13. 7 plus the square root of 13. But wait a minute. 7 plus the square root of 13 doesn't make sense. Because remember, that's a number between 3 and 4. So I don't include that point. So in the end, I only have one point that I'm truly interested in. And that's 7 minus the square root of 13. If I choose a number, the right number, I'll notice I have plus and minus. So I do have a maximum there, a maximum volume. And so the max I can cut away is 7 minus square root of 13 inches. And if you don't mind, I'm not going to plug that in and finding what the max volume is. So it's 11:30. Even though I wanted to start working at 9, it didn't work. But I got started right at 10. It's been an hour and a half. I don't know about you, but I'm starting to get hungry. Are there any generalized questions that you might have that I can solve? Not plot all the way out, but are there any quality questions that I could possibly solve for you? If there's not, I'll call us good. But I hadn't answered so many questions about curve sketching, which obviously takes time. I would have done more optimization. If you want more practice with optimization, my suggestion would be to go to Paul's online math notes. That's a really good source of Paul's online math notes is an excellent source of problems. Sometimes I actually get your quiz questions from Paul's online math notes. So, hint, hint, very useful. Answers written. You do have homework. The only thing you have homework though on is the optimization, because I think you turned in the second derivative test homework on Monday. If you haven't turned in, okay, so you didn't turn in the second derivative test. Alright, the second derivative test and optimization are your homework. If you were supposed to already turn it in, well, she wasn't there, was she? You would be turning in second derivative test and optimization. So yes, Jonathan, you are correct. I apologize to anyone who did not get my count. I tried to send out the best of my count. Yeah, that's right. Second derivative test and optimization. And if there's no other questions, I'll call it good. Just answering a couple of administrative questions if you have any generalized questions about optimization. I don't have time to continue solving them, but I could answer any questions you might have. So remember, picture, choose your variables equation, and then differentiate and solve. Happy Thanksgiving. I'm just gonna stand here looking like a fool until so you guys go or ask me questions. Looks like no one's asking me any questions, so I'm gonna call it an end. Have a happy Thanksgiving. Feel free to watch this. Um, I'll be in the comments down below, but happy Turkey Day, or happy break if you aren't going to be celebrating Thanksgiving.